Hey, Year 11s. It's so nice to see you. Thank you all for coming. I know this is off timetable now, and you're doing this purely, purely to do some chemistry with me, which is so nice. This is off timetable now, and you're doing this. Oh, it's very muffly, isn't it? Let's unplug the microphone. Unmute. That should be better. Is that better? Should be better. Unmute. That's loads better. Yes, that's loads better. 1,000 times better. Right, guys, let's crack on with the lesson. So, by the way, thank you, Meryl. Thank you, Julian. Thank you, Nick. Thank you, Emmeline. Thank you guys for coming. I really, really appreciate it. I was really, really worried in case I was going to do the lesson and nobody would show up and it'd just be me talking to myself. Thought it'd be really sad. But it's nice to see you guys. You make it worth it. Right. Okay, guys, let's crack on. So this is AS Calcs lesson 14. So the first thing we need to do is we need to review our PPT homework. So let's insert our PPT. Let's go for AS Calcs homework, and it's going to be in PPT. Be nice if I just made that bigger. PPT homework, there we go, open. So I just want to quickly review these. I've got my calculator on standby, and we can crack on. Right. Thank you. Oh, no, you guys know that I will always support you guys with these things, and you know, I'm so sad that I've lost you guys now, and it's nice to do this with you. Right, so we know that it is x over y times a million. There's our parts, and of course, added a different zero there. And we know that in reality, this is kind of given as solvent. This is kind of done as solute. Yeah, but really wanted over what it's in, wanted over total volume. So here's our solute, here's our solvent. They've even given it as in grams. Nice and easy. 0.15 over 2,000 times a million. I'm just going to put 10 to the 6 to save me the time. Total on my calculator, 0.015 divided by 2,000 times by 1 exponential 6 gives me 7.5. And the answer is B. Amazing. Dead easy. Nice, easy start. Next. The solution contains, they've flipped it round. So we've done the mass of solute in 1 kilogram. So we've got mass of solute over 1,000 grams, because we're in grams in the question, times by 10 to the 6 gives me 33. Reorganize. Yeah. Divided by 10 to the, oh no, we have to do divide first. So multiply both sides by 1,000. Divide it by 10 to the 6, and that should give me the mass of solute. I can then run it straight forward and to check my answer. So 33 times 1,000 divided by 1 exponential 6. It's not 10 exponential 6, it's 1 exponential 6, isn't it? Yeah. Gives me 0.033. Just to check that, now, because that spits out 0.033 grams, let's just check it. 0.033 over 1,000 times 1 to the 6. Yeah, so 0.033 divided by 1,000 times by 1 exponential 6 gives me 33, which is exactly what I've got there, which is great. Next, cold water fish require a minimum of 8 parts per million of oxygen by mass in water in 1 kilo. So we've got what is the minimum mass of oxygen, question mark, over 1,000 grams, because we're in grams in the answer, times by 1 exponential 6. Yeah, it should actually be, by the way, 1 times 10 to the 6. It's what it should be, and that's going to equal 8. Reorganize, times 1,000 over 1 times 10 to the 6. So I'm going to get 8 times 1,000 divided by 1 times 10 to the 6 gives me, oh, that's made a mess. Oh, What have I just done there? 8,000 divided by 1 million gives me 8 times 10 to the minus 3, which is that one there. B. Amazing. Next. Okay, 0.06 grams are found in 5 kilograms. What is its ppm? So that's great because I need to convert that to 5,000 grams. Yeah, so 0.0006 over 5,000 times a million times 10 to the 6. 0. Got to count my zeros there, guys. That's the trap. That's a trap. They're looking for a calculator error. Yeah, divided by 5,000 times by 1 exponential 6 gives me 0.12. There's my answer. Let's just check that now. Oh, yeah, no, that's absolutely fine. I like it. Parts per million. Done. Next, what is the concentration in ppm of 20 grams in 6? Right, there's the trap. That now becomes 600 grams. Yeah, so we've got 20 over 600 times by 10 to the 6. 20 divided by 600. Yeah, multiplied by, it's going to be massive. Multiplied by 1 exponential 6 gives me 33,000. Oh, isn't that interesting? Right, guys, that one is far more fascinating because what they're actually saying here is none of my answers, there are 2 answers here and none of them match. There's a really clever trick. The 20 grams of solute is going to be adding 20 grams into it by mass. What is the concentration of 20 grams dissolved in? No, no, that's not right. Guys, that should have come out okay. 600 grams of water. That should have given me the right answer. And I'm dead in between the 2. Isn't that fascinating? Well, let's put in 600. And the problem is if we put 620, it's dissolved in the solute. That's correct. Because it's done by mass. How bizarre. None of them fit. I'm dead in the middle of the 2. I'm at 33,333. It's right in the middle of those 2. How strange. I don't like it. 20 divided by 620. That puts me at the lower one, you see. Isn't that fascinating? It's going to add it, whereas the other one, it can't be less than. Can't be less than. Yeah, I couldn't answer that one. It's really interesting. So what I've done is, plot twist, it's a trick question. Yeah, so hang on a minute. Would you agree that what I've just done is I subbed in the 20 into the mass, giving you a total of 620. When you run that through, you get this one. Yeah, that comes out from that one. Well, you'd never do over 580. You wouldn't ever minus it. So that one's definitely off the cards. So the answer is that one. 25% chance it's right. No. No. The answer is that one. Yeah, they've done a weird trick there of combining it to give you the total mass. Yeah, that's all. They've done it over 620. It's weird. Let's do the next one. What is the concentration in parts per million of moles of methane dissolved in right? So we know that we've got 1,500 grams. We need to get grams. The number of moles is grams over rams. Yeah. Right. I've got moles and I've got rams for methane reorganized. Therefore, moles times rams gives me grams. So 0.5 multiplied by 16.0 is going to be equal to the same as divided by 2. So 8 grams. Yeah. So that becomes 8 over 1,500 times 10 to the 6 gives me 8 divided by 1,500 multiplied by 1 exponential 6 gives me 5,300. And there's my answer. There we go. Done. Next. Determine the concentration parts per million of 1. Oh, that's all right. That's nice and easy. Yeah, 1.5 over 8,000 times by 10 to the 6. This is nice and easy. Nice easy one. God, that's a doddle, isn't it? It's a doddle. I said that word to my year 10s today, and they didn't know what I meant. Times 10 times 1 exponential 6 gives me 187.5. There we go. Done. Next. A solution has a concentration of 1.25 grams per liter. What is its concentration in ppm? Right, so that's 1 in, and 1 liter is 1,000 grams of water. So that just becomes 1.5 over 1,000 times by 10 to the 6 times by 1,000,000. Sorry, I'm late. Oh, it's nice to see you, Manisha. Lovely to see you. 1.25 divided by 1,000 times by 1 exponential 6, and I get 1,250 ppm. Next, what is the literal meaning of a doddle, though? It's exactly as it says. Really easy. Yeah, Google it if you like. My year 10s did. Yeah, setting up this thing as a doddle. What's up, dude? Next, what is the concentration? Trap. Got two choices. Either flip it to grams. Oh, milliliters. Oh, per milliliter. Wow. So that there is 0. Darn it. It's still not right. So first of all, convert 0.5, divide it by 1,000 to put it into grams. Yeah. 0.5 divided by 1,000. Yeah. Shift eng. 0.0005 grams. A milliliter is 1 gram. Yeah, it's 1 centimeter cubed is equal to, so it's 0.0005 over 1 times a million. Gives me that. Divided by 1 is the same number, times by 1 exponential 6. 500. It's 500 parts per million. Tick it if you got it. A solution contains 0.033 grams in a kilogram. Okay, well, that's nice. So that's 0.033 in grams already over 1,000 grams times 10 to the 6. So 0.033 divided by 1,000 times 1 exponential 6, which gives me 33 ppm. Next, a solution contains micrograms. Micrograms. So let's convert the micrograms. 250 micrograms. Divide it by 1,000,000 to put it into grams. It's going to be divided by 1,000,000 times by 1,000,000. It's going to be 200 parts per million, probably. It's going to be 2,250 parts per million, most likely. So if I do 2,250 divided by 1 exponential 6, gives me 2.25 times 10 to the minus 3 grams. And that's in 1,000 grams divided by 1,000 grams, because a kilogram, we're converting that to grams as well. Got to make the units match. Yeah, so that divided by 1,000 multiplied by 1 exponential 6, and I get an answer of, it's not quite the same, 2.25 ppm. Interesting. Next. Right, this was a bit of a nightmare. This is a real exam question now, guys. A real exam question. Oh, wow. How many questions did I give you? Gave you more than I thought. Right. Another halogenoalkane, toxic gas, plants, health and safety, 5 parts per million by volume of gas are harmful. A research laboratory contains this many dm cubed. Calculate the maximum volume of bromine in dm cubed allowed in the laboratory. So question mark over the total volume, 2.5 times 10 to the 5 times 10 to the 6 equals 5 parts per million. So first thing I need to do is do the divide first. Times by 2.5 times 10 to the 5 divided by times 10 to the 6 divided by a million equals. So 5 multiplied by 2.5 exponential 5 divided by 1 exponential 6. And I get 1.25 dm cubed. Isn't that fascinating? It seems like an awfully large amount. 1 liters, no, it's only actually a small thing, isn't it? It's not a lot, and that's a big laboratory. Blood plasma contains 20 parts per million of magnesium by mass. Calculate the mass of magnesium in grams present in 100 grams of plasma. Right, okay. So we've got 100 grams of plasma looking for the mass of magnesium times by 10 to the 6 equals 20 parts per million. Yeah, reorganize. Times it by 100 divided by 10 to the 6. 20 times by 100 divided by 1 exponential 6 gives me 2 times 10 to the minus 3 grams. We're done. Magnesium chloride can be used as a supplement in diets to treat low amounts of calcium in the blood. Suggests one property that makes it more suitable. Interesting. Magnesium chloride versus magnesium carbonate. This one's soluble. MgCl2 is soluble versus all the group 2 carbonates are insoluble. just so you know. Just like to let you know that. Group 2 carbonates, insoluble. Insoluble. Which means you won't absorb it, it'll just come out in your poo. Lol. 1 kilogram of solution contains 2 calcium ions. What is the parts per million? Why the heck are they giving it to... Oh, moles! Oh, I thought it said grams. Right. So I need equal... Oh, parts per million. So I need question mark over 1 kilogram of solution times 10 to the 6 gives us ppm. But the problem is we must be in grams and we've been given moles. Number of moles is grams over rams. Reorganize. Number of moles times by rams will give me grams. The weight of magnesium atom is 40. So 0.1 multiplied by 40 gives me 0.4. That's correct, right? 0.1 times by 40. Gives me 4. I'm an idiot. Gives me 4. There we go. So 4 grams over, so 4 over 1,000 times, times by 1 exponential 6, 4,000 part ppm. Next, in 2006, the concentration of carbon dioxide in the atmosphere was 382 parts per million. This is equivalent, as a percentage. Wow. Okay, eek. So the concentration, so hang on a minute. As a percentage, parts per million. So hang on, we have got 382 per 1 million. That's the ratio. Yeah, we want this as a percentage. Well, percentage is per 100, right? How do I get from here to here? To get 1 million divided by 100, I've got to divide by 10,000 to go from there to per 100. So I just need to divide by that by a 10,000 as well. That's tricky. Clever trick. 382 divided by 10,000 gives me 0.0382 per 100, which is percent. Percent is just per 100, yeah? So that one, B. That's genius. Just do the same thing of how to get, that was per million. The percentage is per 100 / 100 per 100%. So that's really clever. Neat trick, that. Blimey. Who got that one? Who got 13? Blimey. That one would have stumped me back when I was studying it. Blimey. Right. 660 grams. Okay. Question mark over. It's over a kilogram. Times 10 to the 6 gives me 66. Good job, Merrill. That's hard, that. Times 1,000 over 10 to the 6 gives me question mark. 66 times 1,000 divided by 1 exponential 6 gives me 0.066 grams. We're done. Next, a sample of swimming pool water contains parts per million and is equal to a percentage. Right, I've done it twice. Really surprised. Add maths things. Yeah, it's just all maths. Stupid tricks. So we've got 0.482 per 1 million particles. Hang on a minute. This is again as a percentage. Well, I need to get that down to 100, which we now know is divide by 10,000. So I need to get that divided by 10,000 as well. That's the way I see it in my head. 0.482 divided by 10,000. Clever game. Shift eng. 4 zeros. Done. Finished. Is that the end of the test? Nope, it's not. Oh, no. Horrible. The nitrogen dioxide content of air on a particular day was 0. By mass. The density of air was, oh my Lord. Right. We need to get to kilograms because the answer's in kilograms. Yeah, so we've got question kilograms over density per meters cubed. So do we assume 1 meter cubed, which equals 1 kilogram? Because this is kilograms in a kilogram. Kilograms per meters, density of the air per meter cubed. Let's just put it in as, let's just ignore the meters cubed. Let's just ignore it. Times 10 to the 6 gives us 0.150. Just ignoring the meters cubed. It just means that we're treating a single meter cubed, which is equal to that many kilograms. Yeah, Oh yeah, we want the answer in kilograms as well. So reorganize. Times by 1.225 divided by 10 to the 6. The problem is, I might get this one wrong, guys. I apologize if I do. Multiplied by 1.225 divided by 1 exponential 6. Right. 1.84 times 10 to the minus 7. Oh, wow. That's clever, isn't it? There you go. C. Because it rounds up. That's clever. That's a trick, that is. Don't like that at all. Last question? Yes. Next, for safety reasons, the concentration of lead paint should not exceed this. Therefore, the mass of lead in 1 kilogram of paint, right, and they want it in grams. So question mark over 1,000 grams times 10 to the 6 gives me 600 parts per million. So multiply it by 1,000 divided by 10 to the 6, 600 divided by, no, times by 1,000 divided by 1 exponential 6 gives me 0.6 grams. We're done. Finished. Right, how did you guys get on? Hope you guys got on okay. I won't bother collecting your scores. No point. Actually, no, you probably might want to actually put them on. I don't know how much it's out of. You guys can figure that out and then add it to the sheet if you want to add it to the sheet. That'd be great. I would appreciate that. It'd be good for me to keep hold of all this data. Right, guys, today's lesson title. Right, so our lesson title today is, and I'm going to be really fast with this, folks. Yeah, because I've already taken up half the lesson going through the homework anyway. Right, so new. Let's do, so this is empirical formula. Empirical / water of crystallization. Water of Chris. Right. So the great thing is, of course, guys, with this is the same as GCSE. Now, there's a reason why I'm linking these two lessons together, because the process is almost the same. In fact, it's exactly the same. It's just knowing what you're doing. So first thing is, let's do empirical. So everyone in this room already knows that empirical formulae is the simplest whole number ratio. They always love you to define all these. Simplest whole number, and that's key. Yeah, whole number ratio of atoms of each element of atoms, the whole number ratio of atoms of each element in a compound. Now, the method for solving this, I'm actually just going to give you a question to do here, because it makes more sense for me to do this via a question and highlight the methodology that we're doing. So this is where I do need a question, and I've been an idiot and not found myself one because I'm a dope. Hang on a minute, I can quickly find myself one. Won't take me very long. It might take me a while, actually. I tell a lie. You guys are seeing my screen anyway, so I've got a way of finding that. Kept all the sheets, you see, of all the stuff I've been doing with all my classes. And I just did empirical formula with my year 10s. And so I've got an empirical formula homework somewhere. And empirical formulae. Yes, okay. So that's what I'm going to do first. I'm going to do this one. I've got two of these I want to do. Let's go for this one. I like this one. I'm going to screen cut this. New. Yeah, there we go. Edit, copy. Right, so with empirical formulae, the questions are usually very straightforward. I'm actually going to do two questions today for this one. So they give you, oh, I'm sorry, I've chosen the wrong question. Chosen the wrong question. I want one that actually has percentages. That'll do. I'll steal him instead. Sorry about that, folks. There we go. Edit, copy. And lob it into here. Right, so there's a very straightforward method here. So what we're doing is counting atoms. Yeah, so all we're doing is so this is our method steps. Method. So the method is step 1, yeah, percent to mass. We remember these from GCSE. Step number 2 is mass to moles. Step number 3 is divide by the smallest. Divide by the smallest, find the ratio. Now there is a step 4, but you don't always need it. Multiply if fraction. Yeah, and that one needs to be starred because I need to show you examples to this. So first step. Now the great thing is because this is out of 100, we can just flip it into grams. Yeah, so we can just go. So step 1, list the atoms. Yeah, so when I get these questions, I list my atoms. Yeah, P and O. Underneath it, I put the percentages. Yeah, 31.6. Oxygen 65.3. I now add a grams. I now change the percent sign to a gram sign. Now because I'm counting atoms, yeah, in the definition, the simplest whole number ratio of atoms. That's important because that tells me that I need to divide them to work out moles. I need to count atoms, and the ARs come from the periodic table. So hydrogen on the periodic table is 1 and 1, so we're dividing it by 1.0. Phosphorus on the periodic table is phosphorus is number 15 and 31.0, I believe. I'll check that in a sec. And oxygen, of course, is oxygen 8 and 16.0. So we're going to be dividing them by their atomic numbers because we are counting atoms. I'm just going to quickly check phosphorus for a minute. I haven't seen phosphorus on the A-level table in a while. Should be 31.0. There you go, 31.0 there for phosphorus. Nice. Right, so that divided, so that becomes 3.2. So 31.6 divided by 31, 31.6 divided by 31 gives me 1.02. Yeah, next one, 65.3 divided by 16.0 gives me 4.08. Right, divide them all by the smallest. Yeah, 0.1, 3.1, 3.1. Right, so that becomes 1, hence the simplest whole number ratio. 1.02 divided by 3.10, 3.1 gives me 0.33 rounded. That's interesting. So there's my fraction. And then 4.08 divided by 3.1 gives me 1.32. Right, now this is where the fractions come in, because usually this point here is the end of step number 3. Yeah, step number 3 has just been finished. Now, usually you'd get like whole numbers like these. You might get 3.01, but that's still just 3. Yeah, you round those. The problem is you can't round these. Yeah, you can't do that. With the fractions, we need to multiply. And this is the rules now you get for A level. Yeah, so if you get x 0.5, then what you do is you double it times by 2. And what that will do is, of course, that will then give you a whole number. Yeah, it'll just become x3, I believe. I don't know. You get the point. If you get x 0.33, which is a third, yeah, by the way, in reality, this 0.5 is a fraction, and you're multiplying it by the denominator. That's actually what you're doing. Yeah, so because this 5 there is 1/2, you multiply both by the denominator and it'll make it a whole. This 0.33 is 1/3, so you multiply that by the denominator. Yeah, so that's going to become times by 3. Yeah, if you got a quarter, x 0.25, then that's 1/4 multiplied by the denominator, and you end up with a whole number. Yeah, what happens if you end up with something like, let's go for what happens if we got x 0.66? That's this number here. Yeah, this number here is 2/3. So you're going to multiply it by the denominator. Yeah, it's a rather neat trick. It's all maths games in reality. Yeah, you're just multiplying by the denominator each time, and that'll make it into a whole number. So in this particular scenario, I've got a third. Yeah, we know that that represents a third. So multiply everything by 3. So that now becomes 3. Yeah, 0.33 times by 3 gives me 0.99, aka 1. Yeah, and then 1.32 times by 3 gives me 3.96, aka 4. Final answer, H3PO4 empirical. Yeah, not complicated. This bit might be an extension for you guys, recognizing them as fractions when you have a decimal. It's rather an odd game, this. They get harder with Ale because these fractions now appear, and knowing how to deal with them is kind of important. Right, so once we've gone to empirical formula, What I now want to do is show you empirical formula linked to molecular. Yeah, so empirical and molecular. And now I'll show you a question for this as well, and molecular. So find another question on my sheet. That's actually not a good one for this. That's a bit irritating. Let's try a different one. I'm definitely going to have one. I had loads of empirical formula homeworks. Yeah, there you go. Let's choose that one. Let's just take this one. No. Let's take number 5 since it's nice and easy. Edit, copy. I'm just adding the extension on of molecular and empirical, because the questions usually become, and at A-level, they always now blend. Always. They are always going to include both in your questions. Yeah? It's really annoying this when it won't let me do certain things. Right, I'm just going to put a box around. I'm just going to go to that one there. Right, okay. So, determine the molecular formula and the empirical. Let's do both. List the atoms. Deduce that amount of carbon and this amount of hydrogen. Right, it has 85.7% carbon and 14.3% hydrogen. Usually says the rest hydrogen, you just do 100 minus 83. 85.7, it's very easy. So, switch the sign to mass. Yeah, this is really easy. Now get to moles. Carbon weighs 12, hydrogen weighs 1. You guys will recognize all of this from GCSE. 0.7 divided by 12. Yeah, that gives me 7.14. Hydrogen, 14.3 divided by 1, which gives me 14.3. Right, divide them all by the smallest, a very common step that's often forgotten if you haven't practiced. Yeah, and that gives me 1. 14.3 divided by 7.14, and I get the answer as 2.00. So the answer is 2. So my empirical formula is CH2. Now here's the next bit. So that brings us to the empirical. No fraction multiplier needed because they all came out as whole numbers anyway. But then it's given me the MR. Now what we realize is whenever we have an empirical formulae, whenever you have empirical, something like this, this is molecular, the actual number of atoms of each element in a compound, versus the molecular. What you've done is, in this case, this is the empirical, the simplest whole number ratio. What we've done is we've divided it as many times as possible to make it simple. And in this case, divide by 2. Well, how do you work out that divide step if you've only got the empirical? Well, the way that you do it is by working out the formula mass. If you work out the mass of the empirical, which is carbon is 12.0 plus hydrogen at 1.0 times 2, which gives me 14.0. This is the weight of the empirical. Yeah, it told us the actual thing weighed 84 in the question. Yeah, the actual thing, the real one, CXHY, weighed 84. Well, we can work out what the divide or multiply step is. We just divide that by 14, and we're going to get the multiplier. 84 divided by 14. 84 divided by 14 gives me exactly 6. So now I multiply all the numbers by 6. C6H12, because we're going to multiply the 2 by the 6. Yeah, so final answer. So now, by the way, at A level, the only thing you're ever going to get is this. Yeah, at GCSE, they just like you to run empirical and often stop there. At A level, they never do now. We never want the empirical. The empirical formula is pretty useless, to be fair. So, by the way, that's the formula of cyclobenzene. So, no. It could be hex-1-ene or hex-2-ene or hex-3-ene or cyclohexane. Could be cyclohexane. Anyway, so nice easy trick there, nice extension. It's still GCSE. Let's now go to the water of crystallization. Because how does that connect to this? Students often forget or often miss the fact that there's a connection between water of crystallization. Crystallization. Da, da, da. So in water of crystallization, you're given this rather odd formula. I'm just going to rewrite that to make it clearer. Yeah, you're given these odd formulas. Sodium sulfate dot X H2O. And you're asked to calculate a value for X. Yeah, now this dot here, The dot means trapped with. Yeah, trapped with. And in this case, trapped with ... Yeah, so in this case, we've got trapped with water. Yeah, we've got inside the crystal. Yeah, we've got a solid here with water trapped inside it. Yeah, this is hydrated sodium sulfate .xH2O. Now, what we realize is we can drive out the water. We're going to heat this stuff. Yeah, we're going to heat it, and we're going to drive out the water. What that means is the mass is going to decrease. Now, people often ask me, why do I link these empirical to water crystallization? Because the process is the same. Let's just quickly go and have a look at, let's go and grab a question. Water crystallization homeworks. These are all from my year 10s, by the way. Water crystallization homework 1. I had to write my own for all of these things. I got a couple wrong, I do believe. But let's just grab the top one. Grab the top one. There we go. Edit, copy. Paste that into here. Right. So we've been given a question now. And as I said, these do relate. Yeah, there we go. So it says, I'm going to scroll over to this side. Hydrated potassium sulfate is heated till constant mass and the water leaves as steam, the remaining mass. Right, so what they've done is, this is where the empirical thing comes in. Instead of listing the atoms, what we're going to do is list the compound and water. Because what we're going to do is, we need to count particles. X there is the number of water particles. Yeah, water molecules if you prefer. So I need to count them. The way we count them is moles. And now because we realize that there's an invisible one here, we need to get that to the number 1 as well. We're running empirical. Yeah, so the first thing is we've got 45.6 grams of the hydrated. We then heat it, and we then have 34.8 grams of the anhydrous. That 34.8 is the important bit, because that is the weight of the solid without the water. Right, now what that means is the mass of the water is the difference. Yeah, 45.6 is the hydrated potassium sulfate .xH2O. Yeah, that's this guy. And then we're going to heat it, and what happens is the water leaves, and we end up with potassium sulfate anhydrous and H2O. So over here is 34.8, and the leftover mass, the mass lost, is the mass of water. So we need to do 45.6 minus 34.8. 45.6 minus 34.8 gives me a mass of 10.8 grams. Right, there's my mass of water. Let's lob that in there. 10.8 grams. Right, now I've got to grams, I can now get to moles. That looks like gas. Now I can get to moles. Well, everyone knows that water is 18.0. But potassium sulfate, no idea. Potassium, I believe, is 39.1, I believe. A-level periodic table. Nope. Potassium, 39.1. There it is. Got to be really careful on this. So potassium, 39.1, plus sulfur, 32.1 as well. Amazing. Plus the sulfur at 32.1, plus oxygen at 16.0 times by 4, and the potassium's times by 2. So 39.1 times 2 plus 32.1 plus bracket 16.0 times 4 gives me what? That doesn't make sense. 39.1 plus 39.1 plus 32.1 plus 16 times 4 gives me 174.3. Get rid of that stuff now because you can't use that. That's going to lose me a mark. 174.3. Right, let's run the maths. 34.8 divided by 174.3 gives me 0.199. Actually rounds to 200, amazingly. 10.8 divided by 18 gives me 0.6. Divide them all by the smallest. And of course, we all know that the 0.2, we always knew that this one was going to spit out 1 because It was 1 in the equation. It's 1 in the question. It was 1 there. Yeah, and this, of course, spits out 3, so x equals 3. But we're running the same process. Get from percentage to mass, mass to moles, divide by the smallest. It's the same process. Yes? So, is there any extensions for this? No, not really. That basically brings us to the end of the lesson. It covers all my learning objectives amazingly. Suddenly realized it suddenly went really quickly at the end. Thought the empirical was going to take ages. Right. I've got a little bit of time left. I'm going to just do a couple more questions. I think I made a mistake on some of these as well. I'll probably have to check on my maths again anyway. Yeah, don't know. Maybe I won't. I think I'll leave it there for today. You guys have had enough of me anyway. Right, guys, on the classroom, I will set you an empirical formula homework and a water crystallization homework, just to solidify everything, and then I'll go through the homeworks next lesson, and you can ask some questions if you get stuck. But otherwise, it has been amazing to see you. Thank you so much for coming. Do a solid shout out to Meryl, Emmeline, Nick, Manisha, and Julian. Thank you guys for coming. I really appreciate it. I hope you guys all have a lovely rest of your day, and I will see you all soon. Take care. See you later, guys. Oh, nice to see you, Hermione.